Chapter 4, Part B, Thermal Expansion, Sample Problem 2. In this example, we study the effect of thermal expansion on a configuration which consists of different materials uh, come along each other and fixed at both ends at supports. Let's look at the configuration first. As you can see, there is a solid cylindrical shaft made of aluminum. At the midsection, you can see a solid cylindrical shaft which consists of made of bronze, and at the very last, you can see the solid cylinder of stainless steel, which all center to each other and confined at two fixed support at the both ends A and D. Let's talk a bit about material properties and then approach our problem. Stainless steel, as you can see in the figure, originally called rustless steel, and that's due to almost 11% a composition of uh, 11% of chromium, which is a composition that prevents iron from rusting, while aluminum is a silvery white metal, which is a 13th element of periodic table. And the aluminum, one interesting fact about aluminum, it's the most widespread metal on Earth, and at the same time, the ratio of strength to the weight of aluminum it's pretty high, relatively high, and that's made it a very useful metal in transportation industry due to the low weight and high strength. Mhm. And our last material is bronze, which is one of the most popular material in shaping and creating sculptures. Let's back to our problem. You can see the configuration of different length and size and materials of the solid cylinders centered to each other, and experiencing at the beginning T1 is 70 degrees Fahrenheit. If we increase the system temperature of the system by 40 degrees to reach T2 of 110 degree Fahrenheit, we want to know then what is the average normal stresses in each individual part Mhm, due to that expansion. The very first step to approach this kind of problem with different materials, first we jump to the material property table to see their modulus of elasticity, and also if there is a heat or cooling effect, we need the coefficient of expansion due to temperature. So as we know that for all three materials, let's uh, look at the problem. As soon as we heat the system, there is an expansion of material. There is outward expansion toward the supports due to increase in temperature. At the same time, because it's fixed at both and the support A and D doesn't let it go anywhere, so it's fixed. The same amount of force is applied to the system itself. We call that Fa from support A and Fd from support D. By creating the equilibrium equation, we can easily see that sigma summation of forces at x direction should go 0 because there is no other external forces within the entire system. So Fa starting from left to right Fa minus no nothing, no nothing, Fd equal to 0. So that says Fa is equal to Fd. And let's make it simpler. Fa equal to D. That should go by D. And let's call both of them Fd. And the other component is that due to the fact that the both supports are fixed, delta AD is 0. Delta A with respect to D goes 0. A goes nowhere with respect to D. Mhm. And if we want to apply our equation of delta, delta from force plus delta from heat should cancel out each other. The addition of both of them should go 0. So we do have a negative sign or inward push to the system, and we do have a positive expansion due to increase of temperature. Mhm. So the push wants to uh, confine material as much as it can, and the thermal expansion wants to expand the material. So that's the direction are opposite each other. If we The next step is to just apply the same fact for each individual part A, part B, and part C. And if we have 10 parts, just apply them to those 10. So for the very first part, we can see negative minus FL over EA plus alpha delta T equal to EL. So we have all the pieces of information we need. We know what alpha is, what E is for aluminum. We know what the diameter is, which is 12 inches. We know the length of the aluminum, and we do know that confining pressure, it's a inward push to both ends of aluminum applies if you take that part out of the sample. So in that terms, a negative F, which is unknown, times length of aluminum, which is we have all the uh, parameters in, for example, E is in KSI, kilopound square inches, so we need to convert 4 feet of length to inch. Each feet is 12 inches, so that's just multiplication by 12 over in denominator, while we do have cross-sectional area pi times 6 square times modulus of elasticity of aluminum, which is 10 to 6, and that's to uh, sorry 10 cube ksi is equal to, that's correct, 10 6 psi. Mhm. And then plus 12.8 times 10 negative 6, which is the thermal expansion of aluminum, times different in temperature from 110 minus 70, 40 degree, and times again length of material, but in inches. The next step is doing the same likewise a step for the second material, which is bronze. So every terms remains the same, uh, and just be careful. Thermal is expansion. Force is a negative because it's a push, and expansion due to temperature goes by a positive. Mhm. The same likewise for stainless steel. We do have the same story as we apply our problem. It goes by a negative for force and a positive for expansion in temperature due to temperature. And if you look at to this equation, the only unknown is F. If you add these three together for aluminum, bronze, and stainless steel, the same equation, yeah, and you solve it for F, it just gives you a force of 277.69 kilopounds, and that F stands for FAFB. That's FD. B is somewhere in the middle. FAFD, and that's equal to the force of 277.69 kilopounds. As soon as we have the force, the uh, normal stress is just normal force over axial force over cross-sectional area. So if we do the calculation, sigma aluminum is the same contact force over cross-sectional area of aluminum, and that gives us 2.46 ksi. Do the same mass for bronze, give us 5.52, the same contact force over this time cross-sectional area of bronze, pi times 4 squared, and likewise sigma of stainless steel contact force over denominator pi 2 squared give you 22.1 ksi, which stands for kilopound